Welcome to section 1.2, Functions and Graphs. So your textbook has this interesting idea of how to introduce functions. What's a function? Well, here's a real-life example of a function. Let's say you had a pricing model for how you're going to sell some books and raise some funds. So let's say you had you were going to say $2.50 for each book that you sell, and then $3 for kind of like a mailing fee, like shipping fee. So if a person wanted to buy just one book, then you would, instead of X, you'd write 1. 250 times 1 plus 3 is 550. And so the input would be 1 and the output would be $5.50. You could even plot that on a graph if you wanted to. If someone bought 2 books, then that would be 2 times 250 plus 3, which is $8. And so the input is 2, the output would be 8. If the input is 4, then you could say that this is 4 times 250, and this function would yield $13 as your output. You could write that as input 4, output 13. Input 7, output $20.50. Input 10, output $28. And you get the idea. There it is. You can also think of functions in another way. Like you think about your cell phone. There's actually cell phones and computers and electronics in general work really well on the idea of functions, because everything you do, every input you have, has a very specific output, very well defined. It's not like you're going to press a button and 2 possible things could happen. If you press the exact button in the exact same way, every time it'll work the same way. So if you press the volume up button, then that corresponds to the actual volume being turned up. You press the volume down button, same thing, the volume will go down. If you tap the home button on, say, an iPhone, then it'll display the home. If you hold onto the power button, it turns off or it turns on. Those are the 2 different, and depending on whether or not it's already on or already off, depends on whether or not you turn it on or off. But anyway, the input is here and the predictable output is here. So for this next example, I have a guest speaker. This is my wife, Mrs. Corinne Bergman. Say hi to everybody.
Hey, everybody.
So she's going to help me perform a song called Let Me Clear My Throat. It was put out there by DJ Kool in 1996. And back in the mid-90s or so, hip-hop DJs were actually live performers, and they would try and get the audience involved. So I'm going to be DJ Kool, and my wife is going to be the audience. And so it's kind of models input-output. So it goes like this. Now, if y'all want to party like we do, if y'all want to party like us, let me hear you say, ah, 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 ah.
Ah, 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 ah.
Now, when I say, you say, ah,
Ah,
ah. When I say, hey, you say, ha, hey,
ha,
hey.
ha.
When I say, you say, ah,
Ah, ah.
So we can kind of think of this as a function because every input has exactly one output. Like DJ Kool was a master at what he did, so he let the audience know exactly what to do based on what they heard. So if he said they knew to say ah, and there was no confusion about that. They all responded immediately. And then the next thing he would do, he would get to a part of the song where he'd be like, when I say freeze, y'all stop on a dime. When I say freeze, you just freeze one time. When I say freeze, y'all stop on the dime. Freeze! And then everyone would strike a pose. And so everyone would strike a pose, and some people would flash deuces, and other people would give a GQ look or top model, whatever it was. Everyone was able to kind of do their own thing, and it was a lot of fun. But as soon as they did that, it actually stopped it from being a function and turned it into something that's not a function, because he allowed people choice, and people did different things. So as soon as he allowed people to do whatever they wanted when he said freeze, it's no longer a function. So you can say that a relation is a pairing of all input to output. That's just kind of in general pairings look like that, but a function is a special kind of pairing, such that for each input there is exactly one output. The relation. So let me clear my throat is actually a relation, and that's because the freeze input had multiple different outputs. So let me clear my throat is actually not a relation. Up until the freeze, it is a function. every input has exactly one output. But as soon as you allow for one input to have multiple outputs, then it's not a special function, it's just an ordinary relation. Functions are a special kind of relation. The domain is the collection of all the input values. So here the domain is 1, 2, 4, 7, 10. Here the domain is all the different things you could press, and the input for Let Me Clear My Throat would be these right here, the input. The range would be the collection of the output values. So all the outputs would be $5. All the dollar values here would be the outputs, and all the actions would be the collection of the output values. Some things I want to say about that is that with functions, input has a predictable output. I think I've said it before. It's not a function if any one input has more than one output. So it would not be a function. So this graph right here would not represent a function because, look, you've got one input, 3, 3, 3, and you'd have a couple different outputs. If the input is 3, then the output could either be 5 or 2 or -1. So that's why this graph does not represent a function, because you can see for these inputs, for this one input, there are 3 different outputs. Another thing you'll notice is that function notation is written like this, f of x. You'll see this a bit later. You can say that this is the book notation, f of x equals 250x plus 3, if you wanted to. And it's super confusing because so far we've trained you to think that when you have two letters next to each other, they mean multiplication. Normally you would see this written down, and you might, if you didn't think it was a function, you might think this is f times x. But really, it's written like this, and it does not mean f times x, it means it's a function. It means that x is the input and f is the name of the function, and you just pronounce it f of x. I want to go back to this idea of not a function. Sometimes with graphs, you can tell whether or not they're functions by giving them a vertical line test. So functions, if you want to figure out if it's a function, then all the vertical lines you could possibly draw will cut the function 0 or 1 times. So, but then on the other hand, if you can draw a line that cuts the function more than once, then it's not a function. So here we could draw lots of lines, and for every single line you could possibly draw, it would only cut the function 0 or 1 times. Specifically here, 1 time. But this is not a function. Look, you're able to draw a vertical line. This is the vertical line test. You're able to draw a vertical line and cut the function more than once. If you can do that anywhere, then it's not a function. Because look, this input, a value of, say, -1 would have 3 different values as outputs. Although you could draw a vertical line here, and you wouldn't necessarily cut the function more than once. If you draw a line here, then yeah, you would cut the function, you would cut the graph more than once, and so therefore it's not a function. I'd like you to do this one. I'll do the examples E and F first. You can see you can draw all these vertical lines, and even if it flat lines or it changes, it's still not a function. Sorry, it still is a function. Yes, it is a function. So it cuts the function 1 time for each of these vertical lines. And here, this is a strange looking graph right here, and maybe I'll zoom in a little bit, but you can see that if I drew a straight vertical lines here, vertical lines, we cut it only once, and even right here, very carefully at -1, I'm going to draw a vertical line, and it's going to go through the function here and not here, because this is an open dot. It's not including this. This part of the graph is continuous all the way up through here, but it goes up to this boundary point, but does not include this boundary point. So when you draw a vertical line here at -1, it only cuts it at this. It only touches the function at this point here, -1. Does not touch it here, although the boundary here and everything to the left of it is right here, and everything to the right of it is up here. So you go ahead and figure out if you think that this is going to be a function or not. So domain and range. Domain and range are actually is super tricky, and so I'm going to try and explain as much as this as you see. So so here, maybe I'll start with this particular example. So the domain is going to be all the x values, all the input values here. In this function, it only exists from -4 up to positive infinity. If you try to put a -5 in this function, it wouldn't work. You wouldn't get a real number. The -5 plus 4 is -1. Take the square root of -1, and it's just really difficult for us to do right now. We don't have any numbers that are the square root of -1. So you can't. So if you had an input of -5, it would not have an output. So because -5 does not pair with an output, doesn't produce a value, you can't include it in the domain. Only these numbers are going to produce values in the domain, from -4 and higher. If you put -4 in, you get the square root of 0, which is, you can calculate that is actually 0. So if you wanted to express the domain in terms of set notation, set builder notation would look like this: all x such that x is greater than or equal to -4. That's showing you that it's from -4 all the way up to positive infinity, and that's how you would express the domain right here. The range are all the output values, a collection of all the output values. And you can see the output values start at 0 and they go up as high as you want them to. Eventually this will get as high as you need. So you can say that the output values start at 0, including 0, and go up to a positive infinity here. That's in set builder notation. That's x, all x such that x is greater than or equal to 0. So here in the straight line, you can input any number you want. The domain is -infinity to positive infinity, and when you do that, you'll get out every input will have exactly one output, and so the range is going to be from -infinity to positive infinity, because you can go down as far as you want here, and you'll touch all the blue lines. You'll go up as high as you want here, and you'll touch all the blue values up here. So the domain and the range are unrestricted. They are all real numbers from -infinity to positive infinity. And one way in set builder notation that we just talk about that, it would be just this squiggly R, italicized R. It stands for all real numbers. Here, you can also input and output all real numbers. So every x value will produce an output. So therefore, the domain is all real numbers. There's no restrictions, no square roots or fractions that might prevent you from putting a number in and getting a number out. So therefore, you can have the domain is going to be all real numbers, and then the output, all the outputs here go from -infinity up to positive infinity. You can go up as high as you want or down as low as you want to get whatever number you need. So therefore, you can say the range is going to be -infinity to positive infinity. Okay, here things are going to get a little tricky, because here we've got a fraction. And the problem with fractions is that sometimes you could have a 0 in the denominator. What value you're going to have a 0 in the denominator? You'll have a value at +2. If you try and put 2 in for x, you get a 0 in the denominator. So therefore, we have to remove 2 from the domain. To try and put 2 in, you won't get an output. So this input 2 has no output. Therefore, it should not be in the domain. And you can see right here, the domain, it's kind of easier to do in set builder notation. You just say all x such that x is not equal to 2. And every other number on the number line is not equal to 2, and every other number on the number line is part of the domain. We removed 2. Now the way that looks in interval notation is you have to put together these two different pieces. Here's a piece and it ends at 2, and here's another piece and it begins at 2. So you've got this piece here for set builder notation. You've got this piece here for set builder notation. You can see it goes from -infinity up to 2, and then this U, this is actually the letter U. It stands for union, meaning I'm going to smush together this piece and this piece. We're going to consider this one domain because of the two parts that I've created a union from 2 up to infinity, not including 2, from -infinity up to 2, not including 2. Parentheses all the way through, very important. The range is similar. You'll notice that you can get as high as you want or just by getting as close to positive 2 as you want. And you can get to down as low as you want here. But you'll never actually get 0. You can get as close as you want to 0 by going to the right, or as close as you want to 0 getting as you go to the left. But you'll never actually get a y value of 0, no matter what value you put in for x here. So the range is going to be all y such that y is not equal to 0. Again, we have to remove the y value of y. That's what it looks like in set builder, and then in interval notation, you can say we're going to take this piece from negative infinity up to 0, not including 0, and we're going to make a union with this piece here from 0 up to positive infinity. Okay, this one might be a little easier, a little less tricky. If you got this crazy polynomial right here, there's x to the 4th minus 2x squared minus 3. You can put in any value you want for x, and you will get a corresponding value out. So therefore, we don't have to remove any x values. You can just say that the collection of all the input values is all real numbers from negative infinity to positive infinity. Set builder notation, you can just say r, and then you can say from negative infinity to positive infinity using the interval notation here. Now, the range is going to be a little different, because you can see, although it goes as high as you want here and high as you want here, it'll go up to positive infinity. It won't go down to negative infinity. The lowest value you get to is negative 5. And you can see that here. Oh, here's an error. This should be all the y's, y such that y is greater than or equal to negative 5. So here, from negative 5 all the way up. And then you can see in interval notation, the interval is starting at negative 5 and including negative 5 all the way up to positive infinity. Here's a really strange function. It's kind of like it actually is a half circle, and it's defined by this square root. And so you'll notice that the inputs, if you get too low, the value is going to, you're going to get a negative in the square root. It'll be 4 minus a really large number. And so if you get like square root of negative 2 or square root of negative 6 or square root of anything that's negative, you can't have that. You could have something exactly equal to 0. For example, if you put in 1 here, 1 minus 3 is negative 2, squared is 4. 4 minus 4 is 0. So the value of 1 works here. And so you can see 1, that's fine. 1 all the way up to 5. All these values, all these x values produce y values, which is great. So between 1 and 5, including 1 and 5, you'll get values. So this is the domain, every value in between 1 and 5, including 1 and 5. The range, and again, this should be y, that's a mistake. Y is, all y is such that 1 is less than or equal to y is less than or equal to 2. So here you can see from 0, this should be 0. Terrible. 0 to 2 is the range.